Hello, everybody. Welcome to class. Today we are going to talk about the Diffie-Hellman key exchange algorithm, which is actually the first algorithm that belongs into the category of public key cryptography algorithms. So with Diffie-Hellman, you do not encrypt, decrypt information. What you can do is actually to exchange a key over an insecure channel. So the interesting thing about Diffie-Hellman is that it leads to other approaches how to construct cryptographic systems. So after we talked about the algorithm, what we are going to do then is to look into some math that will help us understand how to make the Diffie-Hellman key exchange algorithm um, secure. Okay, so this has to do with finite groups and specifically with cyclic groups. And this leads to the formulation of what we call the discrete logarithm problem. And the discrete logarithm problem is at the heart of the Diffie-Hellman algorithm, as well as other cryptographic algorithms. So let's start. How does it work? So when we have a communication pattern like this one here, so Alice and Bob are connected over an insecure channel. We mentioned already that RSA is incredibly slow. So in a system like that, it would be desirable to have a shared secret, a key, a symmetric key that can be used for some private key cryptography system like AES. So the question is, how do you get that key which is shared between Bob and Alice? How do you actually get that over the network, over the insecure channel without, for somebody to be picked up and eavesdrop who is listening here and monitoring the insecure channel? So here's the algorithm. Here's how it works. And it's incredibly simple and elegant. So that's really the cool thing about Diffie-Hellman. So there are two parameters that Bob and Alice share and send over a network, over the insecure channel. It's a prime number, a really large prime number P, and a parameter alpha. And alpha needs to be smaller than p minus 1. And an additional condition is that alpha needs to be a generator. And this is where cyclic groups come into play. Otherwise, Diffie-Hellman is actually not secure. So, and we are going to see later on what that actually means. What is a generator? So, once these parameters have been agreed upon, what Alice is doing, Alice chooses a private key, which we call small letter a, and it chooses a, out of any number smaller equal to p minus 2. And Bob is pretty much doing the same thing. Independently, what Bob is doing is he chooses a private key, and we call it small letter b, and it's being chosen out of the same range of numbers. So with that, what Alice is doing is she computes alpha to the power a modulo p. And this yields a number capital A. And capital A is a public key. So it gets sent over to Bob. Okay. And Bob, again, it's in that respect totally symmetric. What Bob is doing is Bob is computing alpha to the power of B modulo P, which leads to the computation of another public key, which we call capital letter B. So now B is being sent over to Alice. So obviously, Bob has Alice public key A, and Alice has Bob's public key, capital letter B. So what they do now is they do the same thing what they did before, just with the public keys. So Alice is computing a number which is capital letter B to the power A modulo P, while Bob is computing capital letter A to the power of B modulo P. So see the B that he had here, the B that he had here, this is basically used twice. And Alice is doing the same thing. The A that she has is being used twice as well. Okay. So now comes the interesting thing. The result that both of them yield, both of them get, is the shared secret A key, secret key KAB. So this is kind of the surprise. How come that Bob and Alice arrive at the same result? And this can be proven actually pretty quickly. When you think about what Alice is actually computing, Alice computes, remember this was capital letter B that she got from Bob, and she puts that to the power of her own secret key A, small letter A. So she essentially computes alpha to the power of AB. So Bob is doing something similar. Bob receives capital letter A, the public key from Alice, and puts that public key to the power of his own secret key, B, small letter B, and he also computes, and this is the same result, he gets alpha to the power of AB. So convince yourself that the order in which you compute the different powers here, alpha to the power of A and then to the power of B, or alpha to the power of B and then to A, yields both the same result. And this is how the Diffie-Hellman key exchange actually works. So with relatively simple means, we can agree on a shared secret. And we can afford to use an insecure channel for doing that. So that's a pretty cool thing. And what is even cooler is that the underlying scheme behind Diffie-Hellman actually help us to construct more and even more modern cryptographic systems, public key cryptographic systems. Okay, so here's some supplemental material that I encourage you to actually look into. So the original paper that Diffie-Hellman wrote, they wrote in 1976, and it was a paper called New Directions in Cryptography. And as I already said, it was the first ever published algorithm that was a public key cryptography algorithm. So the paper was published in 1976, and sadly enough, it was the year where I was drafted into the East German Army. It was a very, very sad year for me, and basically a loss of a number of years of my youth, um, which I still look back to with regret. Okay, so the other one is this here. It uses an it's actually a YouTube video, and I encourage you to watch it. It gives an explanation of how Diffie-Hellman works using an analogous system, using colors to explain how this system works and how these one-way functions work. So when you think about it, Diffie-Hellman really relies on one-way function, which means that it's relatively easy um, to compute the power of a number, but it is really hard to determine what the power was actually. So it's easy to say, okay, we compute alpha to the power of small letter a modulo p, and that yields a. And now understand that the attacker, both this parameter and this parameter and this parameter, and you would think that it's really easy to compute back, what small letter a is, and it turns out this discrete logarithm problem is actually not easy to solve. Okay. Excuse me. Alrighty. So this leads us to the discussion of finite groups and eventually of cyclic groups. So why is that? So when you think about it, um, what you want to avoid, you want to avoid that an attacker may just do a brute force algorithm and compute all possible powers of alpha to the power of something and yield a result and compare the result with capital letter A. And in the worst case, it would not take many chances, many different A's to compute small letter A to compute capital letter A. So what you want to have is a scheme where the relationship, the mapping between small and capital letter A is very confused, and this space of possible numbers should be as big as possible. And what does it mean as big as possible? It could be at the utmost as big as p minus 1, okay? And this is exactly what we are going to talk about in our discussion of finite groups and eventually cyclic groups. So we talked about groups before, and remember that groups, the way how we are going to use them in cryptography, they always have a finite number of elements, for one. And in general, a group is a set of elements, and we can apply a group operation on that set of algorithms. So to keep it general, we call this this group operation. Um, we just call it donut for now. And specifically for us, it's interesting as a first step to have a, the multiplication with um, modular reduction. This is of interest for us in the first step. So remember that groups need to obey a number of properties. So first off, if we apply the donut operation to a pair of elements of the group, the results also needs to be in the group, and this is what we call closeness. Okay. Associativity is not that interesting for us, but identity and invertibility are again very interesting. So in a group, we have an element that we call identity element. And the symbol that I'm using here is a 1 to depict that element, but it doesn't necessarily need to be 1 actually. So in a group under addition, for instance, that identity element would be 0, and it's pretty straightforward that in a group under addition, 0 times 0 plus a, equals a plus 0, which is a. Okay. So, and the invertibility is the same thing. We can, similar. So if we apply to a its inverse, or the other way around, the inverse and the operation a, this yields the identity element. Okay. So under multiplication, the identity element would actually be 1. So 1 times an element a is the same as a times the element 1, which is a. And invertibility, an element a times its inverse, or the other way around, yields 1. So, and we have already said in groups under multiplication, in order for the inverse element to exist, we need to have a condition, and the condition is that the greatest common divisor of a and the size of the group plus 1, the order of the group plus 1, this needs to be 1. So the greatest common divisor of a and that number that determines the size of the group, that needs to be 1. Okay, so there's one additional operation if this is fulfilled. It doesn't need to be fulfilled for every group, is that we can, say A donut B is the same result as B donut A. And if this condition is fulfilled, and we are going to see that it is fulfilled for the groups that we are going to deal with here, we call such a group an abelian group. So an abelian group is just a normal group with one additional property, which is commutativity. So for our purposes, the donut operation is, for now, it's the multiplication and subsequent modular reduction. Okay, needless to say, very complicated finite groups. It's are groups with a finite number of elements. So the number of elements in a group we call the order of the group, or we also call it cardinality of the group. And this is being expressed by two bars around the group symbol. So let's look into an example. Let's look into Z9. And for the group operation, we just want to, for the purposes of this class, we want to assume that we have the times followed by modular reduction. So is Z9 a group? It turns out Z9 is actually not a group. So if we look into the group Z9 and its elements, those are the elements here. Okay. So when you look at each of the elements, it turns out that not all of them have an inverse. And invertibility was an important property for a group. And for groups under multiplication, or Z9 under multiplication, we have a number of elements which are elements that do not have an inverse. So those elements I crossed out here in red. It's a 0, which has the smallest common divisor is 9. Here, here for the 3, you know, the common, did I say smallest? The greatest common divisor, sorry. So the greatest common divisor is 3, and in the case of 6, the greatest common divisor is 3 again. This is because, you know, 9 is composed of 2 prime factors. It's 3 times 3. And, you know, if you start sharing one of these threes with a group element, then this group element obviously does not have an inverse. And this is a problem. So at this point, what we can do, we can just throw out these troublemakers. And this is what we're going to do. So we can refine our group. And in order to make it clear that this is a different group than the one that we had originally, we add a star. So Z9 star is composed of the elements and of these elements here, and all of these elements have inverses because none of them shares a factor other than 1 with 9. So this one is indeed a multiplicative group, a group under multiplication. Okay, so here's the theorem. The set of Zn star that consists of all the integers I from 0 up to n minus 1, for which, you know, each element tested, it doesn't share a factor other than 1 with n, those elements form an abelian group under multiplication modulo n. And the identity element is 1. So this is kind of surprising when you think about it. It seems like, yeah, it's okay, you know, it sounds good. But remember, what we did is we kicked out number 3, we kicked out 0, we kicked out 6. And now we can apply our group operation to any pair of the remaining elements, and never ever does any of these operations, whatever you do, yields in a result that is 3, 6, or 0. So this is kind of surprising, and that theorem tells us that this is true. So what I just said, in the remarks here, the theorem tells us that the group is actually closed. Okay, so plus, almost always in cryptography, we use an n which is actually a prime. So when you assume n being a prime, and that's the reason why we are going to replace n with the symbol p for prime. Under this condition, all of the elements except 0 do not share a factor other than 1. So all of the elements are relative prime to p because p is a prime itself. So this is automatically fulfilled except 0. When we talk about these kinds of groups, ZP star, what we actually mean is that we kicked out 0. Okay, so now it's clear that under such circumstances, the order of a group like that is p minus 1. Okay. Okay, so let's expand upon what we just covered and talk about cyclic groups. So what you saw before, and motivated by that, so what you saw before, we computed expressions alpha to the small letter a, alpha to the small letter b, and eventually our shared secret was alpha to the small letters a and b modulo p. Motivated by that, what we can do is we can just compute different powers. So alpha, 2 different powers, okay, and see what we get. So, and you may remember that up there, I already gave you a glimpse. If you put alpha to a power, alpha to the power of small letter a, what you will want to have is a result which is as broad as possible. You want to have a result space that is basically a maximum of what is actually possible. And this is the reason why we look what happens if we compute powers of alpha for different alphas, and of course different powers. So in the first example, let's look into group Z11 star. It has a cardinality of 10, so P is 11. 11 minus 1 is 10. And we choose an alpha which is 3. Okay. So if we compute powers now of alpha, what you see is, alpha to the 1 is 3. And then alpha to the 2 is 9. And alpha to the 3 is 5. And so on. What you see is that at alpha to the 5, to the power of 5, we get 1. And after that, the cycle repeats here. So this is very analogous. You may remember that we talked about a maximum period when we discussed LFSRs. So in LFSRs, you needed to choose the configuration of the LFSRs of the um, feedback of the different flip-flops wisely to actually get a maximum period out. So here you see that we also have a period, and this period is not maximum. So we didn't even get to the power of 6 or 7 or let alone 10. So basically we cover only half of the elements here. And who knows if we, we maybe we can choose an alpha where we get even um, a shorter cycle. So this is undesirable. Okay. So in other words, alpha only reaches 5 elements in the group. So it would be desirable if alpha could reach all of the elements in this group, because we want to make a brute force attack on the scheme as hard as possible. Okay, we do not want to exclude any result space right from the get-go, and thus make it uh, way easier for the attacker, to compute the power. Okay, this leads us to the discussion of what we call generators. So, in order to discuss that, we are going to look into a different alpha. And this time we choose alpha being 2. And we ask the question, how many elements can we reach with this alpha, with this base? So, well, if you do the computation, it turns out that the cycle that we have here is the maximum cycle that we could possibly get, because we actually reach all of the elements. So all of the elements are being reached. This discussion leads us to what we think about an element of what its order is. So the order of an element is basically how many elements you can reach with that base. And we are going to discuss that in more detail in a second. So let me emphasize again that this is the exponent, and we tried different exponents here. And alpha to the power of that exponent, that mapping between the two needs to be non-obvious. Okay, this is another ingredient, and this is also given if we have a maximum order alpha. So one more observation that I added here, I put some numbers in green. So you see, I put this number in green, I put this number in green, this number in green, and this number in green. So I did it for a purpose that is going to become clear later on. But for now, just notice that these elements, they are all relative prime to p minus 1. Okay, so Z11 star is a group that has 10 elements. It has an order. The group has an order of 10. And the elements that you see here, they are all co-prime to the order of that group. Okay. Alrighty. So let's get towards a formal definition of what the order of an element is. So remember, we talked about the order of a group, which is the number of elements in the group. Now we talk about the order of an element. And it would be desirable if the order of an element is equal to the order of a group. And what is that, what we mean by that, the order of an element? So the order of an element A of a group is, and this is important, the smallest positive integer k, such that the element to the power of k yields 1. So it is important to understand that we have the smallest possible positive integer k, such that we get 1 here. Because as we are going to see, for all of the elements, for certain k's, we get 1, but it may not, the smallest positive k here may not be the order of the group. And this is what is desirable for us. So in other words, we may get a k which yields 1 here, but the k is smaller than the order of the group. And this is not what we are interested in. Okay, needless to say, the 1 is the identity element here. And in the example above, the order of 2 is 10. And convince yourself that this basically is equal to the order of Z11 star. Okay. Okay. So with this discussion under our belt, we can now define what a cyclic group is. So a group G, which contains an element alpha, group G, element alpha, with maximum order. This is the key here. So if the order of alpha is the order of the group, if those two are the same numbers, then this group is a cyclic group. So the way how this is being defined is it takes just one element like that. And as soon as an element like that exists, then we call this group a cyclic group. So a cyclic group is just a regular normal group which has at least one element with maximum order. So, and the other part of this definition is that we call such an element alpha, we call it a primitive element or a generator. So these are the same things. And remember, primitive elements, we had primitive polynomials in the LFSR, so you see some parallels here. So it turns out that cyclic groups are at the heart of discrete logarithm problem cryptographic systems. And Diffie-Hellman is one flavor of it, and we are going to look into other flavors after that. Specifically, we are going to look into elliptic curve cryptography. So now in order to understand what a cyclic group is or not and make a quick decision or be able to make a quick decision on whether a group is a cyclic group or not, the theorem tells us that a prime group, so a group ZP star under multiplication is always an abelian finite cyclic group. Okay, so this is important. So as soon as we choose P to be a prime number, we have a cyclic group, which is very convenient. So let's look into two useful properties of cyclic groups that we are going to make use of later on. So given an element A of group G, and G is a cyclic group, what we can say is that A to the power of the order of that group is 1. And A to the power of means actually the group operation under multiplication. I said that already. So when you compute that power, what you need to do is you need to do multiplication with modulo reduction. So, and for a group ZP star, the modulo reduction is by modulo P. So, in fact, this property may lead you to the wrong impression that in such a group, any A is a generator. And this is not true. This first property means that it's fulfilled for every element. And specifically for generators, the exponent needs to be the group order. However, some elements that are not generators will yield this one here with fewer than order of group exponent multiplications. So it will become clearer when we look into another example, which is Z11 star down here. Why some elements need fewer operations here and still get a 1, but they also get the 1 if they use the order. So this property is really interesting for maximum order elements, actually, which are the generators. So we can prove that easily with Fermat's little theorem. Remember that Fermat's little theorem tells us that A to the P is congruent A modulo P. We discussed that in lecture 10, 2 lectures ago, when we talked about some math that is going to help us in public key cryptography. And if we divide the whole thing, we get P minus 1 here, and this becomes 1. And this is what you see here. Okay? So now, it is clear that the order of our group, if P is a prime number, it's actually P minus 1. I said that already. So what we see is here now we can replace that P minus 1 with the order of ZP star. And what we get is actually this here, which is exactly what the first property is. Okay. All right, so this was easily provable. And then the second property, which we're not going to prove, is this: the order of A divides G, the order of G. So order of A for any element A divides order of G. So let's look into that second aspect here using an example. And then using that example, it will be clear what I talked about before, that some elements actually reach the one here before the order of G, power to the order of G. Okay, all right. So example application of that second property. So the order of Z11, and that's our example, Z11, is obviously 10. So 11 is a prime number. So the order of that group is 10 because all of the elements in that group are relatively prime to 11. So what are the possible orders for elements? So the second property tells us that an order of an element divides the order of G. So when we prime factor 10, in this case here, what we get is we get 2 and 5 in addition to 10, and of course we have 1. So all of these are possible orders for elements. And we can show that easily. So we only get those numbers. And here you see a table. And that table shows us the order of each of the elements in that group. And what we see here is that always what we get is either 10 or 5 or 2 or 1. Okay. So this makes the case, and all of these numbers, when you look at it, whoops, they divide 10. All of these different orders divide 10. And this is what the theorem tells us. Not the theorem, this property here. Okay, the order of any element divides G. Now the blue numbers here you see are the desirable ones because those are the generators. Okay. But what you also see is that we have element 3, for instance, which has the order of 5. We have the element 10, which has the order of 2. When you look at those elements, what that means, for instance, for 3, that 3, in this first property here, 3 to the 5 is 10. And then you can, of course, apply another 5 exponentiations, and you get 1 again here. This is exactly what I meant, or here for 10. So 10 to the 2 is already 1. And then you apply another, 2 exponentiation operations, and you get again 1, and again 1, and again 1. And sure, 10 to the 10 also gets you 1. So it is only for the generators where the earliest that they get, the earliest is if this is the order of the group, and then they get 1. Okay. So let's check that for the example that we had here before, of course. So 2 is a generator, and the earliest where we get a 1 here is alpha or 2 to the 10. Okay, all right. So this is the case that I wanted to make. So an interesting other question that we are not going to prove here is how many generators do we have? Actually, it's here where the Euler's function comes into play again. Euler function of the order of the group, it's that many generators that we have. So let's look into an example. So for our group Z11 star, it has an order of 10. So the phi function of 10 is we need to have the prime factorization, remember, and we have only 2 prime factors. We have the 5 itself, we have the 2 itself, with no other exponents, so it's always 1 here. And then this one is 1 smaller. So we have 5 to the 1 minus 1 times 2 to the 1 minus 1, and this yields 4. And as you saw before, we actually have, we actually have 1, 2, 3, 4 generators here. So one way to see the rationale behind that, why is that? Well, it turns out that generators can generate other generators. And this is kind of cool. So generators are generated out of other generators by using elements that are relatively prime to P, like 11 here. Actually, to the order of the group, and you know, Z11, the order would be 10. So which are the numbers that are relative prime to 10? Of course, all the numbers that are not divisible by 2 and by 5, which is 1 here, 3 here, 7 here, and 9 here. So that's the reason why I actually came up with circling them green. So and what you see here is if I put a generator, which in this case was 2, we know already it's a generator. If we put it to the power of any of these relative prime numbers, what we get here is we generate the other generators. So 8 is a generator, 7 is a generator, 6 is a generator. So look at 2, of course, is 6, 7, and 8 are generators as well. How did we generate them? Well, we generated them by putting a generator that we already had to the powers of the elements that are relative prime to the group order. And that said, if we accept that this works, and this of course itself needs to be proven, if we accept that, what that means is that the number of these elements here that are relative prime to the group order, the number of those elements we get from the phi function, and it's phi of the order of the group. So this is the rationale. Again, this assumes that we accept that what we said here, that a generator to the power of these numbers generates other generators. And this itself needs to be proven, and we are not going to do that here. But it's really interesting. That's the reason why I wanted to point this out. Okay, so with this under our belt, we can comment on what the discrete logarithm problem is. So it turns out that cyclic groups make nice discrete logarithm problem crypto systems. This is because we can generalize that principle. We can generalize based on the nature of that function. In this case, it was exponentiation with a generator as the base, and we could compute that function in one direction very easy. It was easy to compute alpha to the power of small letter a and get a result. But knowing the result and the alpha and the modulo reduction prime, it's still hard to figure what the small letter a is. So let's look into an example to illustrate that. So if we say, okay, our prime number is 47 and our alpha is 5, and remember alpha needs to be should be a generator. So of course alpha is element of Z47 star. So if an attacker knows A, capital A, capital B, such that, for instance, A is congruent to alpha to the power of small letter a modulo P, and he can figure out what that A is, then the attacker could solve this equation here. And let me backpedal here. So if the attacker could figure out what the A is, which basically means to solve this logarithm problem. Okay, so all of the other numbers are known. So the 41 is known, this one here, the 47 is known, the P, the generator is known, the unknown is actually the A, and the problem here is really to figure out what the A is. It's incredibly easy to put 5 to the power of A. It's really hard to figure out what the A is given the other numbers. Okay. Okay, so to solve this equation for A, this is what we call the discrete logarithm. Discrete because we also have the modulo reduction. And because of the modulo, this is really hard to do. So in general, if we have given an alpha and a beta and a p, and we try to find this exponent that we need in order to make this equation work, and we solve for the x, we need to solve this logarithmic problem, this discrete logarithmic problem. And this is what the discrete logarithm problem is all about. Okay, so the other part is, remember that alpha actually needs to be a generator so that the result space, which is represented by beta here, is as big as possible. So it should be, with no limitation, be as big as what P suggests. Okay, so if alpha is not a generator, convince yourself that you need to check way fewer cases depending on, what the order of alpha is. And this is the reason why we looked into finite cyclic groups in order to understand what alpha is and what the condition on alpha is. Okay, so this was our today's exploration into Diffie-Hellman and into the discrete logarithm problem. And we are going to generalize the discrete logarithm problem, and then we are going to see how we can use the generalized discrete logarithm problem in order to construct another cryptographic system. And we're going to see how elliptic curve cryptosystems are relying on this problem. And this is gonna keep us busy for the rest of the semester. So thank you very much for chiming in and for listening to today's lecture, and I see you the next time. Thank you. Bye-bye.